So this video is technically for section 1H. There isn't really a formal section here. Instead, what I'm going to be doing is walking you through a part of this classwork 8, applications of limits. Rather than a lecture on this section, I'm going to kind of get you started on these problems. So hopefully you'll be able to finish them and be all ready to turn in your homework. First of all, number 1, please omit that. I apologize. I gave you the exact same problem at the end of classwork 7. And so clearly you don't need to do this twice. So you just go ahead and skip number 1. So there's the first piece of really good news. Let's take a look then, and we'll start with problem 2. It says an object is dropped from a 150-meter cliff, and the height after t seconds is given by this function h of t. I'm actually changing that to a capital H. You'll see why a little bit later. So h of t is negative 4.9 t squared plus 150. And the first question that we're asked is to find the average velocity over the first 3 seconds of free fall. That is between time 0, when the object was first dropped, and time 3, when we want to think about it. We won't be down on the ground yet, but that's where we're going to stop calculating our average velocity. So first of all, if I go over here real quick to Desmos, I have pre-done a few graphs for us. Here's the first one. You'll notice that I've got the negative 4.9 t squared plus 150 graphed. And this is just limiting it. I don't care about negative t values because that would be before the object was ever dropped. And therefore I really only care about t greater than or equal to 0. So that allowed me to start right up here at the top of the tall building, I think, or cliff, I guess it was. And then you can see the object's actually going to reach the ground. It's going to hit the ground here about 5.5 seconds later. The first thing that I want to point out is that the velocity of this object is not the same all the way through its flight, right? Up here you'll notice it's falling pretty slowly. In fact, for the first second, from 0 to 1, its height doesn't change all that much, right? It started at 150, at 1 we're at about 145. So velocity is not very big at first. But in the next second, it's falling faster because it goes further. And so on. It falls faster and faster the closer it is to the ground. That, of course, is just the action of gravity, accelerating the object as it falls. All right, so the first question on our sheet was to find the average velocity over the first 3 seconds of free fall. Let's think for a moment about how we would do that calculation, and then we're going to use Desmos to help us out a little bit. All right, so average velocity let's see, velocity or speed is distance divided by time, right? It would be meters divided by seconds to get meters per second. So I'm going to say the distance in meters divided by the time in seconds will give me a velocity in meters per second. Now to calculate the distance, I'm going to need to calculate the difference between where it started and where it ended, right? Back to here for just a second. At h of 0, we're at 150, and I can actually plot and label that point on the graph. So here we are at the beginning, at the point when time is 0, height is 150. And then I also did h of 3 here. That was 105.9. Plot and label that point. And so if I subtract the height at the beginning and the height at the end, that will tell me how far, the distance this object has fallen. I'm actually going to get a directed distance, and because this is falling downward, I'm going to subtract in the direction 105.9, subtract 150, so that I actually get a negative distance, indicating the downward direction. So let's do that. My distance then, 105.9, subtract 150. That's the ending height minus the beginning height. In terms of time, obviously we know it took 3 seconds, but just so that we can kind of have some sort of a symmetry or parity, I'm going to think my time was 3 minus 0. Again, my ending time minus my starting time. That way I can use the same technique even if I don't start at time 0. All right, that I'm just going to really quickly do in a calculator. And I get negative 14.7, and that will be in meters per second. Again, the negative just says it's falling, and that's my average velocity. Now again, a quick reminder that 14.7 meters per second, it was probably falling slower than that at the beginning, faster than that close to 3, but that 14.7 reflects the average speed or velocity over that 3-second time span. All right, where we're going to go with this, just to give you a sense of where we're going here, is my ultimate goal is going to be to try to ask the question, how fast is it going at exactly 3 seconds? How fast is it falling right there? The problem is, I can't use the technique that we just used for average velocity because that required a distance fallen, or subtracting 2 distances. And I don't have 2 distances to subtract if I'm interested in the exact or instantaneous velocity right at that specific moment at a time of 3 seconds. So we're going to use a method of limits to help us answer that question. How fast is it going right at 3 seconds? Here's how we're going to do that. You will notice in the chart down here, I have several different time intervals for you to work with. First, I'm going to say, well, what if we didn't go from 0 to 3? What if we just went from 1 to 3? Or from 2 to 3? Or from 2.9 to 3? 2.99 to 3, and finally 2.999 seconds to 3 seconds. You can see what I'm doing here. I'm kind of zeroing in, so I'm almost exactly just at that 3-second mark. And what I'm hoping to see in the average velocity column is sort of a pattern or something that I can use to make my best guess at the exact value of the velocity right at 3 seconds. I should be getting close here, but I know I'm not quite there, right? Same idea of limits as we've been working with for this unit. So I'm going to do the next one, and then I'm going to leave you to do the rest. I'm going to use this idea of ending height minus beginning height over ending time minus beginning time all the way through here. So here, my ending time is 3, my starting time is 1. So to do my average velocity, again, it's ending height minus beginning height. So height at the end minus height at the beginning divided by ending time minus beginning time, so 3 minus 1. And if you want to, you can use either a calculator or Desmos. Since I've got Desmos going, I'm going to go ahead and use it. I'll remind you, we already knew the height at 3, right? We already had that before. That was the 105.9. And I could just pop over here really quick and just do h of 1 is 145.1. And then down here, 3 minus 1 is 2. And again, I'll just grab my calculator. and I have negative 19.6. Again, that's going to be in meters per second. So your job is basically to finish that list. Go ahead and calculate the average velocities for each of these time intervals. And then you're going to make your best guess. Make your very best guess, but don't stress about is it right, is it wrong. At this stage, it's your best guess. We're going to actually calculate the limit on the next page. So when you answer question C, what's the limiting value? You're looking at best guess. Looking at the pattern that gets established when you fill that out. As far as interpreting it, remember we kind of talked about that, right? We keep on calculating average velocities, but down here, you're so close that what you're actually trying to get at is an instantaneous velocity right at the 3-second mark. All right, let's take a look at the next page. In order for us to write this as a limit that we can evaluate, we're going to have to make one small change. I'm going to think of the time intervals as t equals 3 minus some value h to t equals 3. And little h represents essentially the number of seconds before 3. So in other words, if I think of my time interval from 1 to 3, 1 is 2 seconds before 3. You can also think of it as just the length of the time interval. It's a 2-second interval. That's a 1-second interval. That interval is 0.1. That interval is 0.01. And from 2.999 to 3 is 0.0001. You do not need to recalculate all the average velocities, just steal your previous work. So from t equals 1 to t equals 3, we already had the negative 19.6, right? And once you filled out that previous chart, you'll be able to just copy that down right here. Clearly our h values here are getting closer and closer to 0. And these values, you've already made a guess at what they're approaching on the previous page. All right, in part E, we are supposed to write an algebraic formula that expresses the average velocity from t equals 3 minus h to t equals 3. And I think we can do that using the same idea of ending height minus beginning height over ending time minus beginning time. Just rewrite that. Ending height minus starting height to get the distance the object fell, and ending time minus starting time to get the amount of time that the object fell for. Well, let's see. This is my starting time. That's my ending time. So the ending height would be h of 3. Subtract the starting height would be h of 3 minus little h, divided by the ending time, which is 3. Subtract the starting time, which is 3 minus h. All right, the last piece of this problem then asks us to write a limit that represents that instantaneous velocity right at the time 3 seconds, and then evaluate that limit analytically. This is how we're going to kind of check and see how good our guess on the previous page really was. Well, we've already said our h, our time intervals, are approaching 0. So if I just take and say the instantaneous velocity is going to be the limit as little h goes to 0 of this average velocity. That is what I'm going to leave you to work out. Clearly the denominator is pretty simple. Don't forget h of 3 we've actually already knew. I think that was that 105.9. And don't forget that to do the h of 3 minus h, you are going to need to plug that 3 minus h in for t in the original formula. Okay. When you do that, you're going to get kind of a big algebra problem. Work through all the algebra, and eventually you should be able to do some dividing out, some cancellation to get rid of the h in the denominator. And that will give you your limit. So that's my hints to get you going there on number 2. Number 3 is actually a very similar mathematical problem, although it's phrased differently in terms of the application. You have just one period of the sine function drawn here. This is actually sine of pi x. So notice the period would be 2 pi divided by pi, or 2. Right? Goes up to 1, down to -1, and then back to 0 again. Typical sine function. Here's something that may be a new definition for you. A secant line is a straight line that joins 2 points on a graph. So we are going to draw the secant line that joins 0.5, 1, right there, and 1, 0, right there. And let's see if I can do a reasonable job here of drawing that straight. There we go. All right. All I want to do is calculate the slope of that line, which of course that's an old hat kind of a thing, right? We've all calculated slopes of lines a million times. Just y2 minus y1 over x2 minus x1. So 0 minus 1 and 1 minus 0.5. That's -1 divided by +1/2, and that should be -2. All right, in the chart, you're just going to continue to calculate slopes of various secant lines. So the one we just calculated is here, and we got a slope of -2. That was the problem we just did. You are going to continue to calculate slopes of secant lines, and you'll notice that the ending point of the secant line stays the same every time. It's always going to be 1, 0. The starting point, however, is going to change. So in the next one, I want to start at x equals 0.75. So let's take a look at that. If x is 0.75, I've got a point on the graph right there. And in fact, if I'd like to figure out what the actual value of the y value there is, I can do that pretty easily because I know the function, right? If I just take the sine of pi multiplied by 0.75, sorry, it's hard to see. I get about 0.0411. Let's go. Does it say? I think it might say. It says keep 6 decimal places, so I'm going to call that 0.75. Oh, I'm sorry. I may be in the wrong mode. Hold on. Yes. I am in degree mode because I was teaching a different class. Let me switch myself back to radian mode. And let's do that again. We want the sine of pi times 0.75. There we go, that's better. So if I keep 6 decimal places, I have 0.707107 if I round off. All right, this again was just 10. And so if I one more time try to draw my little secant line, these are going to get so close together you probably won't even be able to draw the secant line after a little while, but I'll see if I can draw one more here. It's getting really, really close to the curve itself, but you can see it's just slightly underneath it there. If I go ahead and try to calculate the slope of that secant line, I'm going to fill in my y value that I just calculated here, and then just do y2 minus y1 over x2 minus x1. See if I can get this so you can actually see the screen. So it'll be negative 0.707107 divided by 0.25 is negative 2.828. All right, and so once again, just like the last one, what I'm asking you to do then is to finish up the rest of this chart. And on the next page, you'll be able to hopefully guess the limiting value of the slopes. So you'll be looking at your chart. You're going to say, okay, I've got some numbers here, and hopefully you'll be able to start to make a guess as to what those slopes are approaching. But at this stage, it is just a guess, so you don't need to worry, am I specifically right or wrong, just your best guess. I want to talk about interpreting that limiting value for just a moment and talking about what does it tell us about this situation. Well, kind of like the falling objects problem, what we're doing here is we're bringing two things really close together, right? In the falling objects problem, we're bringing the times very close together to try and get right close to that exact 3-second mark. Here, notice that what I'm bringing really close together are the x values. Right? Those x's are getting really close together. So it's almost like instead of finding the slope between 2 points, I'm getting close to being just right at that one specific point. If I come back up to my graph for a moment, and I think about this 0.10 right here, if I didn't have any other points, technically I couldn't find a slope. But what I can do is draw what's called a tangent line. A tangent line, instead of going through 2 points on the curve, just goes through or just touches 1 point on the curve. It kind of skims right along the curve itself. And in this particular case, I'm going to, again, do my very best here at sketching this. In fact, I might even do best without this. I can see both sides. You can kind of imagine a line here that just barely touches the graph here. And kind of does the same thing on the other side. Right? It's going to be really close to that blue line, but just slightly different because it can't actually go through that second point, right? Slightly above there, it would actually be slightly below this one. My drawing's not great there. Okay. That thing is called the tangent line. and it only hits 1 point on the curve. As my 2 points in my chart get closer and closer together, I'm coming closer to having just the 1 point, and therefore I'm coming closer to that tangent line. So all of these slopes that you were calculating should be getting closer and closer to the slope of the tangent line. So that's what you're going to want to say something about in your interpretation here in part C. Is you should be saying, hey, whatever that guess was, I think that's going to be the slope of the tangent line at the point 1, 0. All right, last part of this problem. Write and evaluate a limit analytically, that is using algebra techniques, that represents the same limit that we found numerically in part B. So in order to do this, we're going to kind of take a little piece out of the first problem we did. We're going to say, well, just like on the first problem, we probably want to define an H. So I'm actually going to do that right on here. I'm going to say H is really just the distance between those X values. Just like last time it was the difference between times, the inputs. Here again it's the difference between the inputs or the X values. So my H's are going to be 0.5, 0.25, 0.1, 0.01, and 0.001. Right? I can then think of each of these as 1 minus H. Right? So 1 minus 0.5 is 0.5. 1 minus 0.25 is 0.75, and so on. And so my slope ends up being y2 minus y1. Actually, let's do it this way. So y2 is always 0. y1 is f of this first one, so f of 1 minus h. And then x2 minus x1. x2 is always 1. x1 is the 1 minus h. Okay. That's really how we calculated the slope in more general terms. So coming over to this next page, if I'm going to write and evaluate a limit, I'm going to say the slope of the tangent line would be the limit of this as the h values are approaching 0. And that's the limit that you'll need to actually evaluate to eventually come up with the exact value of the slope of the tangent line. Again, just a reminder, denominator is not hard to simplify. To do f of 1 minus h, don't forget to plug the 1 minus h back into the original function to do that. So again, that's kind of where I'm going to leave you with this, to go ahead and calculate that limit and see if you can figure out the exact value and see how well you guessed. All right, we have one last problem to talk about. If you take a 200 milligram dose of aspirin, the amount in your bloodstream, or at least in your body, my bloodstream might be an exaggeration, but we'll just go with it, after T hours, is 200 e to the minus t over 2 milligrams. You probably recognize this as exponential decay, right? Makes sense. The longer since you've taken the medication, it kind of wears off. and there's less in your bloodstream. We're going to say we're going to repeat the dose every 4 hours and try to write a piecewise defined function for the amount of aspirin, A of t, in your bloodstream after t hours, assuming that you take a total of 3 doses. So I'm going to make a great big piecewise function here because I'm going to need 3 pieces, 1 for each dose. And the first piece is pretty simple. It's just 200 e to the minus t over 2. They gave us that. Now, keep in mind, that's only valid until you take a second dose, because then you're going to have more aspirin in your body. So that's really only going to work until the 4-hour mark when you take another dose. So I'm going to say this is good from time 0 to time 4. All right, right at time 4, we take that second dose, but keep in mind, there might not be a ton of this left, but some of it is still left. So we still have this original 200 e to the minus t over 2. That's still there. But we've now taken a second dose. So we're going to add the second dose in. Second dose behaves just like the first dose. So kind of, I'm going to repeat this. Kind of spreading this out, and that's for a reason. But what I really want to do is start over, but 4 hours later. In other words, I want to shift this 4 hours or 4 units to the right. Remember how you shift graphs left and right? To shift things to the right, you actually have to replace your variable, your x, or in this case your t, with t minus 4. So I'm going to replace my t with t minus 4. Again, the idea here is same basic graph, but it's shifted to the right. 4 units, or in this case, 4 hours. So what's left of the first dose is here. There's my new second dose. That's valid from the 4-hour mark until the 8-hour mark when we're going to take a third dose. So your job is to write the third piece of this. You'll keep your first 2 doses and you'll add a third dose at the 8-hour mark. I just want to comment, that's going to be good for basically forevermore for all t's greater than or equal to 8. As far as this problem is concerned, we never take another dose of aspirin. So we're just going to leave it as t greater than or equal to 8 forever beyond that. All right, in part B, we're asked to graph the function that we found in part A. It says be reasonably accurate with the shape of the graph, but be very accurate at the break points in the domain. So at the 4 and the 8. Okay. I've started this out for us on Desmos. Let me go over to this. And I'm going to turn off some of the stuff we've been using. All right, you can see right here, down here in this A of t, that I've put the first piece of our piecewise defined function in. And you'll also notice that I cheated just a little bit. I have my time interval from 0 to 4, and I included the 4. I'll show you why I did that in just a moment, but let me quickly adjust my axes here so I can see the whole thing. There we go. All right, so there it is from 0 to 4. And you can see right up here at the very beginning, right, 0 to 100. That's to be expected. At time 0, we took the 200 milligram dose, so we should have 200 milligrams at least in our body. Okay. Here's why I did the equals 4 and included that. I'm going to do A of 4 as well. It's about 27.07 if you want to be a little bit more precise. And if I had just said less than 4, it wouldn't have given me that value. Now, technically speaking, this point is not really on the graph, right? Because at that moment, we actually took the extra dose. So when I graph that, I'm actually going to graph it as an open circle. I'm going to put the point 4, 27.07 on my graph. I can label it, but I'm going to put that in there as an open circle. Because at that particular moment, the graph's actually going to jump way up because I took a second dose. Right? So, at this point, I'm going to start drawing the graph, and I'm going to leave you to draw more of it. Back on my paper, we have the 0 to 100 where we started. At the 4-hour mark, we were at about 27, so that would be 25, just slightly above that. I'm going to put an open circle, and over here I'm going to label that 27.7, 0.07 actually, for any reader who may be looking at this later. And then again, that's my very accurate part, and then I'm going to just go ahead and do a reasonable approximation of that exponential decay curve that we saw in Desmos. Right? I'm going to ask you then to add the next two parts of this. The part from 4 to 8 should jump way up right here at 8 because we suddenly, right here at 4, because we suddenly took another 200 milligrams. It'll decay away again, and then it'll jump up again at the 8-hour mark, and then just continue decaying. So I'm going to ask you to add the rest of those. And once you've got your graph drawn and labeled very accurately, this last question should be pretty easy. You should be able to actually find those limits just by looking at your graph. So I'm going to leave you there to complete this assignment, and we'll be back next time. We'll be starting Unit 2.